Okay. Regarding circuit analysis one, so I already shared a kind of a simple briefing of the circuit analysis one. So the slides which I shared you basically cover the very basic electrical concepts and theories which we can easily apply on any kind of electrical circuit. So you are familiar with this basic analysis. So if you are given a kind of a circuit, we basically can apply two methods. So for any kind of circuit, we can basically apply mesh analysis and nodal analysis. So we basically can apply mesh and nodal analysis. So mesh analysis is actually apply Kirchhoff voltage law for the given network. So when you analyze a circuit using nodal analysis, you can simply apply Kirchhoff current law. So Kirchhoff voltage law, it means like if you are familiar with the Kirchhoff voltage law, it's a kind of a, so we can briefly explain that it's a summation of all i's vi equals 0. It means like so the algebraic sum of all voltage drop across a closed loop would be 0. So this should be a kind of a closed loop. So once you apply Kirchhoff voltage law, the algebraic sum of the voltage. Algebraic sum means like a voltage itself is a scalar, but depending on the direction which we apply Kirchhoff voltage law, it may be like a clockwise or it may be to the anti-clockwise depending on the direction of the Kirchhoff voltage law which we apply. So we can identify or we can introduce plus or minus in front of this voltage. If it is a plus quantity, so we can simply assume that the voltage drop is to the direction which we are referring. If it is the negative value or the value with a minus sign, it means like we basically consider it to the direction opposite to the Kirchhoff. For example, so if we are applying Kirchhoff law to the clockwise direction, so whatever the voltages we are measure along this direction can be treated as positive values, and the voltages we consider to the opposite direction or the anti-clockwise considered as negative. So that's why we simply say that this is a kind of algebraic sum of that. So pluses and minus represent the direction or the direction of the voltage drop. So with respect to the direction which we are uh, considering when we apply Kirchhoff voltage law. So when we apply mesh analysis, so it's basically applying this Kirchhoff voltage law. It means like we are basically considering the algebraic sum of the voltage drop across the closed loop system. So it means ideally like for this particular case, normally this whatever the expressions are basically in currents. So if you are considering a kind of a resistive circuit, so if you have multiple resistors and sources in the circuit, once you apply Kirchhoff voltage law, the whatever the equations we obtain from here is basically a functions of currents. But if we consider the nodal analysis, so if you remember, like so then we apply this Kirchhoff current law. So for this case, for the Kirchhoff current law, again this algebraic sum of currents 0. So here the algebraic sum means like if we define a node A like this, so whatever the currents flow into the node can be treated as positive values, and whatever the current flow out from the node can be treated as negative values. So likewise for the scalars, we can introduce pluses and minus to make it kind of a vector format. So this, in this case, once you apply Kirchhoff current law, you can treat the currents which are flow into the node as positive quantities, and the current flow out from the particular node can be treated as negative values. So then for this particular case, you whatever the expression you obtain by applying Kirchhoff current law are function of voltages. So this is the simple summary of this analysis. So you have mesh analysis. Once you want to apply mesh analysis, it means you are basically applying Kirchhoff voltage law. So Kirchhoff voltage law means ultimately you will end up with the set of equations which are functions of current. So if it is a nodal analysis, so you're basically applying Kirchhoff current law. So then the equations you are getting at the end of the scenario is basically a functions of voltages. So it means, so so we can argue like this: if you want to find voltages, so we can easily apply Kirchhoff current law. So if you want to find the currents, so we can easily apply Kirchhoff voltage law to obtain this whatever the unknown currents. So this is the very briefing about the Kirchhoff current law and Kirchhoff voltage law and the mesh and nodal analysis. So keep in mind, if you are given a circuit and if you are asked to evaluate a voltage, so most of the time applying Kirchhoff current law would be the ideal way if it is not a kind of a special set of circuit. So if you want to evaluate the voltages across some elements, so it's wise to apply Kirchhoff. Sorry, if you want to evaluate or if you want to get the current across kind of a terminal or element, it's wise to apply Kirchhoff voltage law. So if you apply the other way around, you may end up with very complex situations. So keep in mind, if your unknown quantity is a voltage, so you can first try with the Kirchhoff current law. If your unknown quantity is a kind of a current, so you can start with Kirchhoff voltage law. So this is a one point which I need to emphasize during this discussion. And you can go through a couple of examples which I highlighted in these slides which I shared. Again, like so the next thing which I want to highlight here is actually, so we have two types of devices. One is called active devices, active or elements. So the second model is passive elements. Okay, whatever the component which we are referring this circuit analysis to basically covers this passive element. So if you have resistors, if you have inductors, if you have capacitors, if you have diodes, so those are basically passive devices. So if it is a kind of a op amp, transistor, So these kind of devices can be counted as active elements or active devices, and resistors, inductors, capacitors, and diodes can be treated as passive elements or passive devices. So then, if you want to indicate the polarity of the passive elements. So if you want to find the polarity of the passive element, so this is the way we. So this, let's assume this is your passive element, and this is the direction of current. So all the time, so this current is simply enters through the positive terminal and leaves from the negative terminal. So this is the voltage drop across this passive element. So if it is a passive element, and you can mark the current as you wish. So once you mark the current, you can simply mark the polarities of this element by looking at the direction of the current. The current is basically flow into the element through the positive terminal of the device or element and leaves from the negative terminal of the device. So then if this is a kind of a resistance, so we can simply say that V equals I times R. Every time keep in mind, once you mark the direction of the current, you can simply identify the polarities of the element. So based on the polarities, you can simply see that. So this is the voltage drop across this particular element. So let's take one simple example. So let's refer the exercise one. So you have one resistor here, then another resistor here, then that resistor, and you have source. So here plus and minus of the source, and the value of the source is 24 volt. So we have R1, R2, and R3. So let's assume that to analyze the current, I'll mark the current flow to the clockwise direction to this. So this is the current. So I'm assuming that the current flow through the network is to the clockwise direction. And based on the direction of this current, I can mark the polarities of these resistors. So here the current flow into the node. So then this becomes plus, this is minus, plus, minus, plus, minus. And here the drop across this R1 is this VR1. Here this is VR2. Here it's VR3. So if you want to apply Kirchhoff voltage law, so I have to clearly mark the direction. So I'm referring to the clockwise direction. This is clockwise direction. So then I can put the algebraic sum of voltage. See, here you have a drop like this. This is your source voltage drop, and let's assume this is E. So then E basically to the clockwise direction, and rest of the voltage drops induced across these resistors are basically to the anti-clockwise direction. So how do we get this direction? So we assume that the current flow through the network is to the clockwise, and based on the direction of the current, so we basically identify the polarities of these resistors, which are passive element for this particular circuit. So then E equals actually VR1 plus VR2 plus VR3. So we can simply say that VR1 is I times R1 and same current flow through the entire mesh. So we can take this I out, which is common for all the voltage drops, then R2 plus R3. This is equals to E. So we can simply obtain the value of I, which is E divided by sum of Ri's. I1, 2. So this is very simple. So then if you get a positive value for the current, we know that the direction of the current flow is to the clockwise direction. If you get a negative value for the current, with respect to the sign convention we adopted here, we can simply claim that the current is to the anti-clockwise direction. For example, if you ended up with I equals 2 amperes, so which means we have a clockwise current of 2 amperes. If you get I equals minus 2 amperes, so it means the we'll get an anti-clockwise current of 2 amperes. So here this plus means that to the clockwise, here this plus represent the direction opposite to the uh, reference. So it's mean basically to the anti-clockwise direction. So this is the way we initially apply the Kirchhoff voltage law. So to apply Kirchhoff voltage law, you should be able to find the individual voltage drop across these elements. To find the voltage drop, so you have to identify the polarities of these passive elements basically. So how do you identify the voltage polarities? Actually, it's based on the direction of the current. So we assume that once you mark the direction of the current is basically enter to the positive terminal of the node element and leaves from the negative terminal. Based on the direction of the current, we can easily mark the polarities of these elements. Once you mark the polarities of this element, we can simply apply Kirchhoff voltage law and find out whatever the unknown quantities here. So similarly, you can apply for Kirchhoff current law as well, like in the slide. So they basically explain the Kirchhoff current law and how do you apply the current to this one. And keep in mind, so if you have two nodes, let's assume if you have two nodes. So here the voltage is V1. So we have two nodes. So we have element, electronics element, or passive element. So we have node A and node B. So the voltage at node A is VA and VB for the node voltage for the B terminal. And if you have current I, so we can simply say that. So we can apply the Ohm's law, V equals IR. So V is actually now current is flowing into the node like this. So then this become plus, this become minus based on the passive sign convention. So this is passive sign convention. So based on the passive sign convention, we identify that this polarity is plus and this polarity is minus based on the direction of the current. So then V is the voltage drop across this element, so which is actually VA minus VB. So this is the voltage drop across this element equals I times R. So then I is actually VA minus VB divided by R. So the potential, this is the potential drop, this is the potential drop across the element. So VA minus VB is the potential drop across the element, and R is the resistive value of the particular element. So you can easily get the current flow through the element as a potential drop or the voltage drop divided by resistance. So then you can find the currents. Or as we highlighted is, if you have a network, if you are planning to apply nodal analysis, so it means we basically label all the nodes with voltages X. So if you have 5-6 nodes, we just denote the voltages at each node as V1, V2, V3 and so on. And then you can apply nodal analysis. So whatever the nodal analysis, then what you will end up with all set of equations which are functions of VIs. So VIs the voltages at different nodes. So you can simply go through the exercise 3 and get a kind of a clear idea about this.